A lot of it is stuff we've already dealt with. Like if we don't know moles per liter is molarity by now, we're sort of in big trouble. But that is a big part of the chapter. And that's involving reactions that happen in solution, just like the ones you did in your lab last week. That was a reaction that took place in solution. And you use the molarity to figure out the number of moles of copper sulfate in that one. And so that we're going to come back to that again and again and again, because that is basic chemistry, figuring out the amount of reactants, the amount of products expected, and all that, balancing equations, all that good stuff. No matter what phase we're dealing in, solid, liquid, gas, we're still going to be doing that. So these are the different types of solutions. And you may be surprised to find out that, I mean, the one we're most familiar with is like dissolving a solid into liquid, but there's lots of other solutions too. Like the air you're breathing right now is a solution. It's a gas, it's a solution of gases, but there is a solvent, a gas. One of the gases is a solvent and all the other gases are solutes. Remember that solvent means the principal part of the solution, the one that's there in the largest amount. So for air, what would the solvent be?
Nitrogen.
That's right. Excellent. Yeah, nitrogen is about 80% of the air we're breathing. So basically what we're doing is we're breathing in a solution of nitrogen. We can also dissolve gas in a liquid whenever you drink a carbonated beverage of any kind. That is CO2 dissolved as gas dissolved in a liquid. Anytime you have a beer or wine, that's also a solution where you have a liquid dissolved in another liquid. And of course, probably some solids in there as well. The earth is covered by this, probably the solution there in the highest amount on earth, salt water, where you have a vast number of both gases, including oxygen. I mean, fish couldn't breathe if oxygen didn't dissolve in water. And so it's got gases in it, solids in it, liquids in it. Gases can also dissolve on solids. You may be surprised by that. But palladium and platinum both dissolve a really high amount of hydrogen on their surface. And that's one of the reasons they're used as accelerators of reactions. You see catalysts made of platinum and palladium all the time, because they absorb gases on their surface and then allow those two gases to come in intimate contact with each other, which speeds up the reactions. There used to be mercury in dental fillings. I'm pretty sure they've gotten rid of that because that's not such a great idea. But mercury, of course, is a liquid at room temperature, and then it would be dissolved in silver and other metals to then be used as fillings. And then finally, we can have solid-solid solutions. Any alloy, and everyone's sort of probably familiar with an alloy, it's just two metals or three mixed together. That is a solution. Whereas something like bronze is an alloy of tin and copper. And when you alloy them together, it's actually harder than either one of them by themselves. And the same is true with brass. You probably have like brass candlesticks or something like that in either your house or your grandfolks' house or something like that. That is a little shinier than bronze, and that's because tin has been replaced with zinc. So that is a copper solution of the zinc.
Here, was the mercury, isn't that, I mean, it's toxic, so I'm curious, was there any adverse effects with the dental fillings of mercury?
I don't know if there really was a big problem, but I mean, since mercury is toxic, generally it's more toxic when it's linked with an organic molecule, like a methyl group or an ethyl group, something like that. But just, yeah, just by itself is not a great idea. But it wouldn't leach that much because it was dissolved in the other metals. So I think it was just mainly taken out just as a precautionary measure. But you can actually, that's an interesting question. You should probably look that one up, because I'm not sure if there ever was, like, you know, cases that were known to be taking place because of that. That's a good question though. So these are some of the definitions we'll be dealing with. We're talking about solutions. So soluble makes sense. That's just a solute that can dissolve in a particular solvent. Like we say, sodium chloride can dissolve in water. Something that's insoluble doesn't dissolve in that particular solvent. Like sodium chloride does not dissolve in octane, for instance. Octane is super nonpolar. Sodium chloride is super polar. And so they do not interact well with each other, so they don't dissolve. Now, when we're talking about soluble and insoluble, generally we're talking about solids into liquids. And when we're talking about two liquids that don't dissolve in each other, we say they're miscible or immiscible. And to the right, we can see oil and water. There's a little bit of food coloring in the water, so you can see it. You can see the separation a little better. But since oils generally interact with each other through London dispersion forces, they're nonpolar. Water interacts with each other through hydrogen bonding and dipole-dipole interactions, much stronger interactions. So water is much more stable when it's interacting with itself than when it's interacting with oil. And oil is much more stable when it's interacting with itself than attempting to interact with water. And so the two phases then separate. So these are some of the some solutes in water, and we'll talk later on, particularly in the workshop tonight, about solubilities, how they change with temperature. Because in this particular instance, this is at 25 degrees. And most solids increase their solubility as water goes up in temperature. So that's why, for instance, you can dissolve a lot more sugar in hot water than you can in cold water. So have a look at the different things that are highly soluble in water and what are the same about them. What's similar about the really, really soluble substances? We've got calcium nitrate, we've got glucose, sodium chloride, sucrose, all super, super soluble. What's similar about them?
What's similar about them is the solubility is like the value on the right side is way higher than any of the other ones.
Why is that?
Does it have something to do with how ionic they are?
It does. It does. They're either really ionic or actually slightly not super, super ionic. Notice that calcium carbonate is not soluble in water, because there we have a +2 and a -2 come together. So we have a really high amount of charge brought together. So that water is difficult to break that really, really strong interaction. Calcium nitrate, on the other hand, is extremely soluble. And that's because we have a +2 and 2 -1s, which make it a little easier, actually quite a lot easier in this case, for water to break those bonds. Sodium chloride is just a +1 -1, as we know. And then what's similar about sucrose and glucose? They're not ionic, but they're very, very soluble. What's similar about them? Other than they're both sweet. So we have glucose here and sucrose there. What's similar about those two molecules?
They have covalent bonds, or is it just glucose?
No, they have covalent bonds.
Okay.
Benzene's got covalent bonds. Benzene is not soluble.
True.
Benzene's not very soluble at all.
Is it the polarity because they're so polar?
It is the polarity. Excellent. Yeah, notice
And
they
water's
both have a lot of oxygens. Glucose has 6 of them, and sucrose has 11 of them. They both have a lot of oxygens. And when you have a lot of oxygens in a molecule, you generally have a very polar molecule. And so really polar molecules dissolve in really polar solvents very well because they both have dipole-dipole interactions. And in the case of glucose and sucrose, they both have oxygens covalently bound to hydrogens. So what can glucose and sucrose do as well as dipole-dipole interactions in water? What else is available to them in terms of molecular interactions?
Hydrogen bonding.
That's right. Yeah, glucose and sucrose can hydrogen bond like a mo. So that's why they're even more soluble, because not only do you get dipole-dipole interactions, you get hydrogen bonding as well. And so you get very, very soluble, very, very high interactions between the solute and the solvent, which is what you want for it to be soluble. So let's talk a bit about saturated and unsaturated solutions. What is a saturated solution? Excuse me. How can you tell if you have a saturated solution?
Things no longer dissolve. You could see the particles build up.
Yeah, that's right. Yeah, like look at this solution over here. Oops, let me go back. If you look at the solution on the right, it's got a ton of salt or whatever it is. I think it's sugar, whatever it is, solid on the bottom, white crystalline, whatever it is. The whole bunch of it on the bottom. So what that means is basically that water can no longer dissolve any more solute. And so a saturated solution is one where if you add any more solute, it's not going to dissolve. It's just going to sink to the bottom. But what we have to remember is that that doesn't mean there's nothing happening in this solution. On the contrary, what's happening in a saturated solution is that some of those crystals that are on the bottom are going into solution. And as they go into solution, some of the crystals that are in solution then fall back out. Because basically what's happening is that all the water in that solution is basically bonding with solute. And there really isn't any capacity to bond with any more solute. And so, and there's no space available either. And so if we add more crystals, some will go into solution, but when they do, they will knock something that was in solution back out. And so basically you will just keep the same amount of solute in solution. And so we use an equilibrium arrow, which is sort of something we really haven't used before. Anyone know what, when you have a reaction with arrows going in both directions, what does that mean?
Also reversible.
Right, that means the reaction could go in both directions. And that's what's happening here. In one direction, we have added solute going into solution. But then in the other direction, we've got solute that was already in solution coming back out and forming crystals. And so we have competing reactions happening in both directions when we have a saturated solution. And remember, the saturation point of every different solid is going to have a different solubility. And solubility is generally given in grams per 100 mils. That's the general way we define solubility. So every solid is going to be different. And it's going to depend on the temperature. Because like I said, the higher the temperature, generally you can dissolve more stuff, because we start having molecules moving around faster. And when they start moving around faster, water, there'll be more space in between the water molecules for solute to go into. And not only that, you break up some of the interactions between water molecules and allow water molecules to then bond more with the solute. So both those things causes the solubility to increase generally. Gases generally become less soluble as the temperature goes up, because gases, well, they like to be gases. And so the higher, and we know that with temperature increase, we know from the kinetic theory of gases that gas particles start moving faster and faster and faster. And as they start moving faster, they start getting to the top of the solution and then being released as a gas. So the hotter your solution is, the more gas is going to be released. And anyone who's ever tried to open a warm Coca-Cola has probably noticed that. Not a whole lot of gas left in solution. So most solids will have more solubility with temperature, but not all of them. Some solids actually, like salt, for instance, its solubility doesn't really change a whole lot. It goes up a little bit. Some solids have a huge increase, and we'll see that with the workshop tonight. And then, as I mentioned, solubility of a gas goes down pretty dramatically when you increase the temperature. You get those active gas molecules moving around. They get so active, they just leave. So Henry's law, dude named Henry, and so the law, he noticed that if you had a bottle, and he looked at, so if he had a bottle with a liquid in it, and there was gas dissolved in the liquid, you would be able to dissolve more gas in the liquid if there's a high pressure of gas on top. So basically what he's saying that the high pressure of the gas on top of the liquid basically is forcing more gas to dissolve in the liquid. And that's what's happening in a can of soda. Whenever you open it up, you hear that sound, right? That is because there's a high amount of pressure of CO2 on top of the liquid in the can. And that's to keep the CO2 that's in solution in the soda, keep it in solution. So the minute you open it, it releases that pressure. And you notice that you know, if you leave that open can just sitting on a counter, it will go flat after a period of time. So where that's important for exchanging gases in the lungs and breathing is that when we breathe in, we now have a higher, what this is called P for partial pressure. So the pressure of oxygen and the pressure of carbon dioxide. When we breathe in, we have a higher pressure of oxygen than in our bloodstream. And so that oxygen passes from the gas in our lungs into the alveoli, and then into the capillaries in the lungs, into your bloodstream. So you have a higher pressure of oxygen outside the blood than in, and so the oxygen moves in. When you breathe out, you have a higher concentration of CO2 in your blood than you do in the atmosphere. The concentration of CO2 in the atmosphere is very low. although getting higher. And so since you have a much higher concentration of pressure in your bloodstream of CO2 when you're breathing out, then it goes from the blood back through the other way. And then you exhale the CO2. And that cycle just keeps going over and over and over. So basically gas and basically all molecules will go from where they're higher in either pressure or concentration to where they're lower in pressure or lower in concentration. And so Henry was the first to notice this. And it's important because it allows us to breathe, which is a pretty good thing for it to do. So any questions about Henry's law? It can be broken down basically as, yeah, gas goes from where it's high in pressure to where it's low. Okay. So one of the ways of measuring solutions when you have really, really low concentrations, there's a lot of different ways we measure solution concentrations. We can measure it in mass over volume as a percentage. Like for instance, if we were to dissolve 10 grams of sodium chloride in 100 mils of water, we'd say it's 10% sodium chloride weight by volume. Or we could also put it in terms of mass over mass. So that same solution would be, let's say, 10 grams sodium chloride in, we put it in 100 mils of water. So then our total mass is now 110 grams. So the mass of the sodium chloride would be 10 grams out of 110 grams. And so it would be like 9.1% sodium chloride mass by mass. We use those sorts of methods for determining concentration when we don't particularly care about a reaction. Like for a lot of solutions in the hospital, for instance, you'll have glucose there in terms of mass over volume, or sodium ions or potassium ions will be there in a certain mass over volume, or liquids will be there in percent volume. We really only use molarity or moles over liters when we're doing reactions. When we're doing reactions, it's really helpful because then we've already got moles right there. And so we could easily figure out how much volume of different reactants to add together to make a reaction happen. But if there's not a reaction happening, we generally aren't interested in the molarity, and we're more interested in masses. Now, when we have really low masses, we generally use things like parts per million and parts per billion. And those, you've heard of ppm, maybe not ppb, but the really, really small concentrations are parts per billion. So those are all mass units when we talk about ppm and ppb. Like for instance, we're talking about the amount of lead in drinking water in Flint, Michigan. We're talking about parts per billion. We're talking about grams of lead in grams of solution. So here's an example here. Cobalt is actually, you require some small amount of cobalt in your diet, but as you can see, not a hell of a lot. The concentration in cobalt in your body is 21 parts per billion. What mass in grams of cobalt is present in a body having a mass of 70 kilograms? So where would we start with that particular example? you want mass in grams. So what are we going to write down first?
$21 parts per billion.
No, we'll do that first. Okay. So 21 ppb.
And then did you try to convert that?
Basically, that means, yeah,
grams?
that means 21 over 10 to the 9th. Because that's billion has 9 zeros in it, right? So 21 over 10 to the 9th times 70 kilograms. Now we want this answer in grams. So then I would convert that to grams. So 1,000 grams is 1 kilogram. That gets rid of my kilograms. I've got grams left. And so my answer would be 21 times 70 times 1,000 divided by 1 billion. So how many grams is that? Anybody? So grams of cobalt, what would that be? No one brought a calculator?
My calculator automatically gives an exponent. So
Okay, I'll take an exponent.
1.47 times 10 to the negative 3.
1.47 times 10 to the negative 3. There you go, grams. Now, how many significant digits should you use?
3. Or no, 2. Because it's
2,
21
right?
ppb.
Because it's 21 ppb. So
So-
yeah, so 1.5
0.5.
times 10 to the minus 3. Or 15 milligrams, 1.5 milligrams. So that's not a lot of cobalt. So you don't really need to go seeking it out in supplements because you don't need that much. So in stoichiometry calculations, we're basically remember, whenever we do a stoichiometry calculation, we're just looking for moles. So if we have a mass of one of the substance, then we use the molar mass to find out how many moles. But if we're given a volume of a solution, then we use molarity. And so that's basically a shortcut, because if we have molarity, that work of converting grams to moles has already been done. So if we have a solution, we don't need to look up the molar mass of hydrochloric acid or aluminum nitrate or whatever it is that's dissolved in solution. That's already been done for us. We just use the fact that it's moles divided by liters to figure out how many moles there are. And then we just use our balanced chemical reaction, which is always the first thing we do in these situations. And then we go ahead and figure out the problem. So one thing we haven't talked about is something called equivalence. So equivalence is also a mole, but it's not a mole of a particular substance. It's a mole of charge. So when I dissolve sodium chloride in water, if I have a 1 molar solution of sodium chloride, that means I have a 1 molar solution of sodium. I also have a 1 molar solution of chloride ion. So basically I have 2 equivalents from that one ionic compound. And based on whatever the ionic compound is, I could get more equivalents than that. So when we're talking about equivalence, we're just meaning charge. And so that'll come up tonight as well. So the other thing sort of want to introduce is dilution, because this is something that if you've worked in a lab, you've done this a lot, because there's certain solutions that we use all the time, like, you know, sodium chloride solutions, potassium chloride solutions, phosphate solutions, whatever they are. We use them a lot. And so it would be really hard work to make up a fresh solution every time we had to use one. What's much easier to do is make up a very concentrated solution, not quite saturated, but close. We make a very concentrated solution, and then we just dilute it when we need some. And we call those stock solutions. Whoops, go back. So those are called, stock solutions. So if I have, like, let's say a 5 molar solution of sodium chloride, for whatever buffer I'm making or solution I'm making, I'm not going to need it at that's a really high concentration. So I'll just dilute it with water and make 50 millimolar or 100 millimolar or whatever it is I need. And so remember, whenever you dilute something, the only thing you change is the volume. The volume is the only thing you change. The amount, the moles of solute stay the same. So if the moles of solute stay the same, that means that the initial concentration times the initial volume that you remove from it, so that's my stock solution, is also going to equal the final volume times the final concentration. So as the volume goes up when you dilute something, the concentration goes down, which makes sense, right? I mean, if you dilute something, the concentration is going to get less because you're keeping the moles the same, but you're increasing liters on the bottom, you're increasing the volume. And so the molarity is going to go down. So this is a pretty easy one to remember, but we're going to be using dilution a lot. So just remember that when you dilute, the moles don't change. And since concentration is moles per liter times liters equals moles. So anytime you multiply concentration by volume, you get moles. And so if the moles don't change, that means my initial concentration, initial volume, got to equal the final concentration, the final volume. We're going to do that a lot with the gas laws as well. So I'm going to sort of speed this up because solvation, we sort of talked about it a little bit. That is the process where ions, or whatever the solute is, gets surrounded by water molecules, and it makes interactions. The water makes interactions with the solute, and so it's either going to be ion dipole, 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 hydrogen bonding, whatever it is. When you add all those interactions together, it's going to be higher, more energy than whatever interaction was keeping that solid together. So if it was sodium chloride, that's an ionic bond keeping those things together. And so that's going to be stronger than that single ionic bond. And so they're going to dissolve. So these are some of the terms we use when these things are dissolving. Now, electrolyte is a new term you've probably heard of. You know, whenever you see a commercial for Gatorade or something on TV, they're always talking about electrolytes. Electrolyte is just an ionic compound that dissolves in water. So sodium, potassium, chloride ion. These are like common electrolytes. Like in the hospital, when you get an electrolyte panel, basically it's the concentration of all these different ions in blood, because you don't want a dramatic change in the electrolyte concentration that could affect things like cardiac activity. So a strong electrolyte is something that ionizes completely when you dissolve it in water, like sodium chloride. When I dissolve sodium chloride in water, all of the sodium becomes sodium ion, and all of the chloride ion maintains being a chloride ion. On the other hand, when I dissolve something like acetic acid, which is an organic acid, remember, an organic acid looks like this. We've got this carbon double bonded to oxygen, and then single bonded to oxygen with a hydrogen. And so this hydrogen here is the one that gets lost. And then we're left with H plus, and this becomes negatively charged. So this does ionize in water, but it doesn't ionize completely. Only about one molecule in 10,000 actually does this, ionizes, loses the hydrogen at the end and converts it into a proton. And we know that as the concentration of protons, H plus goes up, the pH goes down. And so that's what makes it an acid. So that is a weak electrolyte. So we get some ions, but we don't get very many. So we call that weak electrolyte. Now, a non-electrolyte doesn't ionize at all. So when we dissolve sugar in water, sugar has all covalent bonds, and none of them break when you dissolve it in water. A weak electrolyte, like this one, also has a covalent bond, but it's a weak covalent bond, and it will break. A strong electrolyte has ionic bonds that break. And so we're going to deal with weak acids and strong acids in the next chapter. But a strong electrolyte basically will be able, the original way that was determined was, does that solution conduct electricity? And so basically, if you had a battery, put in a couple of wires, and then hooked it up to a light, a strong electrolyte would be able to move charge from one wire to the other using these ions. And so the light would glow, and that's a strong electrolyte. You put a weak electrolyte in there, and the light would be very, very dim, but you would get a few ions moving back and forth. And then with a non-electrolyte, you'd get nothing. The light wouldn't come on at all. Water is a very, very, very weak conductor of electricity. There is some ions in water. We have H plus and OH minus occurring naturally in water all the time, but they're there in such vanishingly small concentrations that it really doesn't do a very good job of conducting electricity. So these are some properties of solutions that we haven't really dealt with yet. One of them that would be familiar for those people in the medical field is osmosis. Now, what does osmosis mean? Well, just like I was sort of mentioning before, how gases, solutes, other sort of molecules will go from areas where there are very high concentrations and go to one where they're very low concentrations. Now, osmosis is the process where solvent molecules will pass through a membrane to a place where there is a lower concentration of solvent molecules. They'll pass through the membrane, but the solute particles can't. And a classic example of membrane is just basically a cell membrane of cells in our own body. The cell membrane in your body, what is represented with these two lines here, basically will allow water to pass through relatively easily. But ions like sodium and potassium are kept out. Potassium is kept inside the cell and sodium is kept outside the cell. And there's actually special proteins, receptors on the surface of the membrane that actively pump sodium out and potassium in. So the osmosis that takes place is that solvent molecules can pass through this membrane, but ions, sugars, all that kind of stuff can't. So what we see is a pressure that takes place. We call it osmotic pressure, where solvent molecules are going to move from a more dilute solution where there's fewer solute molecules and move to a more concentrated solution where there are fewer solvent molecules. So wherever there's less solvent, that's where solvent is going to move to. So if you have a cell would be very, very concentrated. You have a whole lot of things, a whole lot of ions and everything else inside the cell. So water is going to move basically from the outside in, unless you have equal concentrations of solutes inside and out. And then you have basically no osmotic pressure. So osmotic pressure is where is solvent going to move? Is it going to be actively moving in or actively moving out? And the way we determine that is by measuring something called the osmolarity. Now, osmolarity, the word molarity is right in there. So osmolarity is reporting the total number of particles in a solution. So all of them. So iron, salt, sugar, everything. So because all of them are solutes and all of them will have a certain osmotic pressure. And so the osmolarity is equal to the molarity times all of the particle types. So we have to add all of them together to determine the osmolarity. Okay, and we got a question about osmolarity in the problem set tonight. So why osmotic pressure is so important is because when your kidneys fail, your kidneys are actually the main things doing this job in your body. They're the ones filtering the blood and using osmotic pressure to remove waste. And if there's extra water, remove that as well. And so whenever you have a loss of kidney function, you need to basically replace that function with a machine. So here we have a dialysis machine, and what's inside of it is a series of membranes, just like, not quite exactly like what your kidney would have, but would do basically the same thing. Would allow waste material to pass through the membrane and allow water to either leave and go into solution or go into the blood, depending on what the osmotic pressure of the blood is. So we call that hemodialysis. Hemo for blood and then dialysis for basically doing this osmotic cleansing of the blood. So
There's actually another
sure.
interesting level. I don't know if you're interested, but the bath of fluid that is flowing in the opposite direction that the blood is flowing through the dialysis is actually what controls the molecules passing through the membrane.
That's
the
right.
membrane's like the door that they can go through, and then depending on how much calcium or sodium or bicarbonate or whatever they're putting in the bath is what makes it happen. Interesting.
Yeah, no, that's a good point. Yeah, because so in that machine, so here's what we'd have our membrane. So on one side we would have the blood, and on the other side we would have the dialysis fluid. And so basically, whatever concentrations of ions you would want in the blood, you would put in the dialysis fluid. And so if the blood had a lower concentration of the ions or whatever it is you wanted, they would move from the fluid into the blood. And if the blood had a higher concentration of those things that you wanted, they would move from the blood into the dialysis fluid. So basically, by the end of it, the blood and the dialysis fluid would have the same concentration of all of those ions that you would allow to move back and forth. So yeah, it's a really good point to to point out. So this basically shows you what happens to red blood cells in different solutions, to show you what osmotic pressure can do. So if red blood cells are placed in an isotonic solution, now an isotonic would mean you have the same osmolarity inside the cell and inside the solution. So the concentrations of everything would be the same. So in an isotonic solution, they would look like this. They'd look normal. You'd have water moving into the cell, you'd have water moving out of the cell at the same rate, and it would keep the same shape. But if you put it in a hypertonic solution, hyper meaning higher, basically this means there's a lot more ions and everything else outside the cell. So when that happens, water is going to move from the inside of the cell out because there's more solute outside and less solvent. And so solvent molecules are going to move to where there's less solvent molecules. They're going to move out. And what happens to the cells, they're all going to shrivel up as they lose water. And a lot of times we think that must be because salt is like getting into the cells and everything. No, it isn't. It's just water is moving from the inside out. And so they shrivel up, the volume decreases because the water is moving out. And in red blood cells, we call that crenation. Now, the other thing that can happen, if we were to put red blood cells in just water, like no salt at all, that would be like a hypotonic, hypo meaning less. That would mean we'd have basically no salt at all. And so there'd be a much, much higher concentration of solute inside the cell. And so water molecule is going to go where there's a higher concentration of solute. And so water is going to rush into the cell, and actually so much water gets in that the volume increases till just like a balloon pops. And we call that hemolysis. And that can happen a lot. I mean, I dealt with thousands of plasma samples working in the lab, and quite a number of them would be hemolyzed because they just weren't handled properly. At some point, they weren't in the right solution, and so some of them just popped because water just rushed into those cells and broke them. Okay, so I am going to, here we go. So I'm going to give everyone, any questions about that before we start the workshop? Let's check the chat. Molar mass. So any questions before we get together? I'll give everyone about 5 minutes to take a chill, and then we'll come back together and start with number 7. Hopefully, should I put it in the chat? Does everybody have workshop number 7? C? No?
Yes.
Yes.
I can just put it in there just to be on the safe side. Okay, so this first one, I think everyone eventually figured it out. But what I sort of wanted to show was how to use Pivner to figure out everything else. So that's what I just start with that. So I just start with PV equals nRT, and then I try and figure out, well, what is it that I'm trying to calculate here? And so basically, I'm trying to figure out the final volume. And the pressure changes, and the temperature changes, but the number of moles stays the same. So in other words, the only things that stay the same are the number of moles and R, which is because it's always the same. So basically what I just do is then convert that to PV equals NR divided by T. So what does that mean? Well, that tells me that P times V divided by T is a constant, because N is a constant, the number of moles doesn't change, and R never changes. So whenever I multiply pressure and volume and divide by temperature, I get a constant, meaning that if P1, V1, T1 is also equal to NR, well, then that means that P2, V2 times T2 is also equal to NR, meaning they're equal to each other. So instead of having to memorize whatever that particular gas law is, you just derive it whenever you need it. So now all I need to do is solve for V2, because that's the question, right? The question is the final volume, or the second volume. So now all I need to do is multiply each side by T2 and divide each side by P2. And then there's my reaction. There's my setup. So V2 is then just equal to P1, V1, T2 divided by T1, P2. I didn't have to memorize it, which is nice, because I had trouble memorizing things. As you memorize these things, I find I get them wrong a lot. Like I'll flip something. If I derive it this way, I generally don't get it wrong. And the other nice thing is you can use whatever units you want for pressure, as long as they're the same. You can use whatever units you want for volume, as long as they're the same. But temperature always has to be converted to Kelvin. Always, 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 always. So then I think most everyone I talked to got 7.1 mils, right? I think everyone got that one.
Yep.
Yeah. Yeah, so one thing I also wanted to point out was the reason we have two significant digits is because of the initial volume, not because of the temperature. The temperature actually has three significant digits, and I'll explain why. Because you take 25 and we add 273.15 K to it, right? So then when we do that, remember, when we're adding numbers, we stop at the end of whatever the smallest number is. And so in this instance, when we get 298.15, these three digits are all significant. So our temperature actually has three significant digits, not two. So it took me a while to get that myself. All right, so for number 2, where did people start with this one?
Checking to see if it was balanced or not.
Yep, always check that. Excellent. And it turns out I wasn't total meanie. It actually is balanced, right?
Yeah. And then so we
At first, it looks a little tricky because you've got 4 chlorines here, but you've got 2 there. And so initially the thought is, well, it's not balanced. But yeah, it's easy to forget that there's 2 there as well. Right. So then what did you do?
So then, because we're looking to find liters of chlorine gas.
Mm-hmm. And is chlorine gas a product or a reactant?
Chlorine gas is a product.
Right.
Yeah, product. Yeah.
Product here, right?
Yeah. And then it says how many liters of chlorine gas at 24 degrees Celsius and 0.950, you know what I mean, atmospheres can be produced by the reaction of 124.0 milliliters.
What's the first calculation you do?
So what we do is do 124 milliliters times, and then it'll be 1 liter over 1,000 milliliters, because we're looking to find liters. So we're going to convert milliliters to liters.
Right.
And then after that, the second conversion would be times 0.750 moles, I think.
Yep.
Molarity? Yeah, moles.
Over liters. Right.
Over
exactly.
liters. Yeah. And that
gets
cut out
rid
the
of
liters.
milliliters. That gets rid of liters, and you're left with
Mhm.
moles
And
of
then it'd be
HCl.
0.093 moles.
Wow, that was a lot easier. I thought you had to put like moles of chlorine over moles of hydrochloric acid.
Trust me, I did that
You
too.
have to do that next. That's the next step.
Yeah.
Oh,
That's the next step. So once you have moles of reactant, you convert that to moles of product, because in stoichiometry, it's always moles to moles, right? So now, how do we get from moles of HCl to moles of chlorine gas? What do we multiply this by?
You multiply it by the, what do you call it? The ratio, right?
Right, the molar ratio.
Yeah, the molar ratio.
Where do you,
yeah,
where do you
yeah.
find that though?
So you'd look at 4 HCl, and then you'd look at the CO2. So it'd be 4 and into 1.
Right, so it's 4. For every 4 moles of HCl, you only make 1
1
mole of chlorine gas. And we
chlorine
want to
gas.
solve for chlorine gas, so we put that on the top.
Yeah.
Right. So that gives us the moles of HCl cancel, and it gives us chlorine gas. So how many
Mhm.
moles of chlorine gas do we have?
Yeah. Give me a sec. Let me read. Yeah, 0.02325 moles.
Yeah, and we don't round.
Chlorine
Remember, we do
gas.
not round until we get to the end. So now that we have moles of product, but we're asked for a volume. So how do we go from moles to a volume?
Uh,
isn't that the molarity?
No, molarity has nothing to do with the volume of a gas.
Oh,
That's the concentration of something in solution. We're dealing with volume of a gas. So what kind of law would we use for gas? I don't.
Piffler, whatever his name is.
Ignorant.
Pivnerd, that's right. Our good friend Pivnerd.
Yeah. Oh yeah, yeah. And
we want to solve for volume,
volume. Yeah.
right? So we divide each side by pressure. So volume is equal to nRT divided by P. And what number is this in that equation? Is it the V, the N, the R, the T, or the P?
then
N, right, number of moles. That's what it stands for, number of moles. So that's equal to 0.02325 moles times R, 0.0820. I think it's 6. I've been using 5. It's actually 6, right? It's more accurate. Liter, atmosphere, mole, Kelvin, times the temperature. What's the temperature going to be?
298 Kelvin.
Right, we had 273.15, so it's going to be 298.15 Kelvin. 298. Then we divide the whole thing by the pressure, and our pressure is right here. So 0.950 atmospheres. And then we just check to make sure that we've set everything up right. So moles cancels with moles. Atmospheres cancels with atmospheres. K cancels with K. And then the only thing we're left with is liters. So that's right. That's what we want. So we just plug and chug. We just put those numbers in our calculator and figure it out. So how many liters is that?
.598 liters.
How many numbers? So I got 598. Did I get to 59870? And then we round to the number of significant digits. How many significant digits should we use?
3?
3.
4.
Nope, 3. 3 is right because there's 3 in the atmospheres. There's actually 3 in the temperature because we add 273 to it. And there's 4 in the volume. And there's only 3 in the concentrations. The lowest number is 3. So we go to 3, we would round that to what? What do we round that number to?
0.60.
Nope. We want 3 significant digits, not
Oh,
2.
0.600.
Now remember, we're rounding only the last number. So the last number is an 8. So we look to the right of it, and it's a 7. So we round that 8 up to a 9.
Oh,
So 0.599 liters. If it was 2 significant digits, yeah, we would just round to 0.60. You're right. And then for any of these, if you wonder if you're at all accurate, remember that around 1 atmosphere and 0 degrees, that 1 mole of gas is about 22.4 liters. So then just take this number of moles of gas, multiply it by 22.4 and see if it's even close. And when I did that for this one, I got 0.52 liters, which is pretty close. So you know you're in the right ballpark. So that's probably pretty good. And it'll be a little bit lower because that's at 1 atmosphere and we have less than 1 atmosphere. And that's at 0 degrees and we have 25 degrees. So in both of those situations, the gas at a higher pressure and a lower temperature will be a little bit smaller. So we know that that's probably fairly accurate. So it's always a quick, dirty way to check your results. If it's close, then you're probably right. All right, what about the third one? Who wants to start with the third? What's the very first thing to do when you've got a question like this?
Write out the formula.
Exactly. You need to have a balanced equation. Without a balanced equation, we don't know what to do. So this is a decomposition reaction, meaning that this is going to break. Oops, let me go back. Meaning that this is going to break up into other products. So we have potassium chlorate. It's going to break down, decompose into 2 different products. One of them we can see is solid KCl. And what's the other one?
O2 gas.
Yeah, it's oxygen gas, which is O2. Exactly right. Now, is this balanced?
no.
Nope. So let's balance it. So someone's balanced it already. How do we balance it? So potassium and chlorine are both balanced. The only thing that isn't is oxygen. So how do we balance that?
I put 2 KClO3 and then 2 KCl plus 3 O2 gas.
Right. So we balance the oxygens by having 2 times 3 equals 3 times 2. So there's 6 oxygens at each side. So by putting a 2 here, then we have to balance the potassium and the chloride. Luckily, they travel together, so we can just put a 2 there. So now that we have a balanced equation and we're being asked, what is the amount of reactant? And we're told how much product we're given. But we're given product in a volume. So what do we need to convert the volume to in order to relate that back to reactant.
Number of moles.
Bingo. Yes, we need to convert that to moles, but how are we going to do that?
Pivner.
The answer to all of our dreams and all of our nightmares, Pivner. Yes, of course. So write down Pivner. And which one of these do we want to solve for? Which number, which letter do we want to solve for?
Would it be V? Or is
We're given the volume.
Oh, never mind. Is it N then?
N, right. What does that mean?
Number of moles?
Number of moles, exactly. We got to solve for number of moles. So divide each side by RT. And there we go. So that's going to equal our pressure. So what, and multiplied by the volume, divide it by R, and divide it by T. So what is our pressure?
Zero point 0.880 atmosphere.
Right. So 0.880 atmospheres. And our volume is in liters, and that's given here is 126. Divided by R, so 0.0826 liter atmosphere, mole kelvins, times the temperature. What's our temperature? Our temperature is 133. Do I just plug in 133?
You have to add it by Kelvin.
Right, we need to convert it to Kelvin first.
406.15 Kelvin.
Right, so you always add 273.15 Kelvin. And so 406.15 K. So we have atmospheres, liters, Kelvin. So the only thing we have left is moles, and 1 over moles is equal to moles. So we have the right units. So that we just plug all these numbers in, and how many moles do we get?
I got a pretty big number. 548,792.4933 moles.
I don't know how you got that.
Yeah, that's why I was like, why is it so big?
So 0.880.
Oh, that's why. It's because I accidentally put Kelvin on the numerator side.
Oh, there you go. Yeah, so I got 3.32727 moles of O2. I actually used 8205 here, so it'll actually be a little bit different. So that's the number of moles of oxygen I got. And remember, you could always check, take 126 and divide that by 22.4 liters. Because we have a really high temperature, it's going to be off, but we're sort of in the right ballpark. So that's moles of O2. So how do we go from that to get us grams of potassium chlorate?
Use the molar mass.
Not yet.
We need the
Oh,
molar.
no. Oh, the ratio.
There you go. Yeah, because that's what we need the balanced reaction for, right? That's the whole point. It balances moles of product to moles of reactant. So we want to solve for moles of product, or sorry, moles of reactant. So we get 2 moles, KClO3, is equivalent to 3 moles of O2. So that gets rid of our moles of O2. But we're asked for a mass. So we want the end with grams. And we want to get rid of moles. So now we use the molar mass. So the molar mass of potassium chlorate is around 122.6 when I looked it up. So that gets rid of our moles of KClO3. And the only thing we have left is grams. I got 271.949 grams. So what do we report as our final answer?
3 significant figures, so 272 grams.
Right. So the 9, that's bigger than 5, so we would 272. Excellent. So, all right, let's look at. So 4 is just, I mean, that is just a limiting reactant problem. So I think that is a balanced reaction. So yeah, so basically here we just we know what the limiting reactant is because you're told you have an excess of iodine. So you just convert that to moles. Figure out how much product you would get using the molar ratio, convert it to grams. So take moles of sodium borohydride, convert that to moles of diborane, which is our product, convert that to grams. That's our theoretical yield. For theoretical yield, but I had 0.4398 grams. That look familiar to anybody? Look about right? For theoretical yield? Someone got the question 4, didn't they? Or have you left already?
You got a different one.
Oh, what did you get?
We did it by moles.
Okay. But you need to convert. So how many moles did you get? Okay, remember, because we don't measure yield in moles. We always measure it in grams. Because we can't weigh moles.
Right. Okay. So we'd need to rework ours a little. We took it one step too far.
Oh, you converted this to moles as well?
Yeah, we did everything to moles.
Okay, so what,
we
that's
just need to
fine. So
rework it.
what did you get as a percent yield then? Because we should have got the same answer.
67.1.
Yeah, exactly. Yeah, you just divide it moles by moles, and I just divide it grams by grams, but you get the same answer. Right? Because they're both
Oh, okay.
related to each other. Yeah, you don't
Right.
need to go that far.
Right.
Yeah, but yeah, because yield is always measured in mass. Because that's how we typically measure yield of reactions, is in grams. So that's theoretical yield is always in grams. But yeah, it should get around 67.1% for that.
Do you want us to go back and undo the work that we did?
Yeah.
Or would it be?
No, hey, I mean, you got the right answer, so.
Okay,
So
thanks.
but remember that, yeah, yield is always in mass. So yeah, just for future reference. Now this one is probably new to people. So I think I talked to a couple different groups about it. But yeah, I want to introduce the idea of a saturation curve, because you're going to be seeing these. And all it is just shows you the effect of temperature on solubility for a lot of different salts and other molecules. And so you'll notice that for almost everything, the solubility goes up as the temperature goes up. And solubility is generally given in grams of solute over 100 grams of water or 100 mils of water. It's the same thing, since the density is 1 gram per mil. So to figure these questions out, you'd look at the salt you're given and the amount. So the first one is sodium nitrate at 30 degrees C. So we look for the sodium nitrite line, and it's this one. Then we go down to 30 degrees, which is here, and we see where the saturation line crosses. And so we go up from 30, we see it crosses about right there, which is pretty much midway between 90 and 100. So the solubility is around 95 grams per 100 mils of water. So if I have 70 grams of sodium nitrate, is that a saturated solution or an unsaturated solution?
Unsaturated?
It's unsaturated, right? Because what this plot is telling us, that is how much solute it takes to make a saturated solution. That's what the saturation line means. So 100 grams of water can dissolve 95 grams. So that's pretty darn soluble. Can dissolve almost the same mass of sodium nitrate in it. So if I have less than that, it's an unsaturated solution. So then the last question is just what's the molarity of that solution. So we just convert grams to moles and mils to liters. And for at least that one, I got 8.2 molar. Now for the second one, now we have ammonium chloride. So we look for the ammonium chloride, and that is this line here. And it's at 50 degrees. So then we just look and see what the solubility is at 50. So here's 50, and we go up to the line. Oh, it's also, so it's 50 grams. So the solubility limit is 50 grams at that temperature. So do we have a saturated or an unsaturated solution?
I believe it's saturated.
So that's saturated, right? It's right at the level. So any more than 50, and it's just going to start crashing out of solution. So it means we can't dissolve anymore. That is saturated. And then you just figure out the concentration, and that, I think I got 9.3 molar for that one.
We got
And then
the
you just
same.
do the same thing for the KClO3. Is look for the line. KClO3 is here. So you can see it starts at it's not very soluble at all, and then gets a lot more soluble as you increase the temperature. So then you look for it at 50, go up, and just like the previous one, around 20 grams per 100 is it saturated. So this is also saturated. Okay, any questions about how to use the saturation graph? Yes.
So I guess I'm just kind of confused. Like for the first example where there's I thought it was saturated because it was soluble in water,
Mm-hmm.
but apparently it's unsaturated. So I'm just trying to figure that
Well, if it's
out.
unsaturated, it also means it's soluble. It just means you could dissolve more in it.
Oh, okay.
So at 30 degrees, so
So
here's our
the-
line. So at 30 degrees, we can dissolve 95 grams in there. We've only dissolved 70, meaning it's unsaturated, and an unsaturated solution can dissolve more stuff. So we could add more salt, more NaNO3 to that if we wanted to, and it would dissolve. That's the meaning of an unsaturated solution.
So
If we have
there
a saturated solution, if we added more solute, it wouldn't go into solution.
So you're saying that they're inversely related.
I don't understand. What's
Like
inversely related?
if it's more soluble, then it's less saturated. Right.
Hmm. If you can
Or-
dissolve more solute in it, it's unsaturated. If you cannot dissolve any more solute in it, it is saturated. I don't know how to put it any differently than that.
Oh, okay.
What?
Yeah, that's what I meant to say, actually. I was
Okay,
just trying to find a relationship if they were inversely related or if they were.
yeah, see, each salt is going to be different. That's the one confusing thing. Every salt is different. Every salt has a different solubility. You can see that potassium iodide is just insanely soluble. And then you have something like cesium sulfate, which is not terribly soluble at all. So every salt is different, has a different level of solubility. It all depends on the salt and it depends on the temperature. And then you have something like ammonia here, which becomes more and more of a gas as you increase the temperature. And gases do not like to dissolve in hot water. So its solubility goes down.
So if you were to give us a problem like this, but use that really low one, Se2SO4 3, with the same, if you needed 20 grams of that at 50 degrees Celsius and 100 milliliters of water. So you see that it won't even hit.
Yeah, that would be 5. So that, yeah, so the maximum amount of cesium sulfate you could add at 50 degrees would be 5 grams per 100 mils.
And so that would be
And 15 grams.
saturated then.
Oh, yes, totally. In
Okay.
fact, you would have 15 grams of salt on the bottom. So 5 of it would go into solution and 15 of it wouldn't. In fact, that gives me an idea for a really good exam question. Thank you.
Sorry. And then when it says how much more solute can dissolve in the solution, so for example, for that, how much more, or would it not be possible because you see that the slope is downward?
If it's saturated, you can't add any more. So the answer
okay.
is 0. But this solution is unsaturated. You can add more.
Oh, okay.
Yeah. All right, let's.
Oh, sorry.
Oh,
Can you
go ahead.
figure? Can you ask? Can you help me figure out how you figure out the molarity?
It's just moles divided by liters.
So
So
there's 7.
So convert this 70 grams using the molar mass of sodium nitrate into moles,
So you just divide 70 by
and then
100.
divide that by 0.1 liters because that's 100 mils.
So you just do 70 divided by 0.1.
No, because you need the molar mass of sodium nitrate to determine moles.
Oh, right. Okay.
Yeah, so you take grams of sodium nitrate, so 70 grams times 1 mole over the molar mass, and then multiply that by 1 over 0.1 liters. That gives you moles over liters. And the molar mass is 84.995 grams. So grams cancel, you're left with moles divided by liters. That's molarity.
Okay.
All right. Oops. All right. Now 6. That's where we deal with osmolarity for the first time. So we're asked for equivalents. We need to provide that many equivalents of sodium ions. So what's an equivalent of sodium ions?
Mole.
It's just moles, right? It's just this is just another word for moles, but it's a special word because it means moles of ions. You wouldn't say equivalents of sodium metal because that's not an ion. But when it's dissolved in water, it is. So then it becomes an equivalent. So if I have half molar sodium sulfate, what's the concentration of sodium ions in that solution? Remember you had a question similar to this on the exam. What happens to sodium sulfate when you dissolve it in water? What does it make?
Sodium ions and sulfate ions.
Right, it makes sodium ions and it makes sulfate ions. And they're both aqueous. But that's not balanced, is it?
No, you have to have a 2 coefficient on the sodium.
That's right. So if I have half molar of this ionic solid that dissolves in water, what's going to be my concentration of sodium ions? For every 1 mole of sodium sulfate, I get 2 equivalents of sodium ions.
So it's 1 molar.
That's right. So my concentration of sodium ions is 1.00 molar sodium. So then if I need 0.0385 basically moles of ions, what do I multiply that by to get me a volume?
Molarity.
Molarity or what molarity? What units do I put in here? Because I want to end with a volume.
The moles per liter.
Where do liters go? Where do moles go?
The moles go at the bottom.
Right.
Liters go-
Yeah. Here it's not, obviously when it's 1, it's not, it doesn't really matter, but it still matters. It means you have to, because it may not be, it's not going to be 1 all the time. So for every 1 liter, there's 1 mole. So we get rid of moles and we're left with liters. So how many liters is that? Or how do we convert liters to, because we want milliliters. So we could just multiply this by 1 more thing to give us milliliters. How do I convert liters to milliliters?
1 liter is equivalent to 1,000 milliliters.
Right, so what do I put on the top? Milliliters or liters?
ml at the top.
ml, right, I put ml on the top. So it's 1,000 milliliters for 1 liter. So 1, 2, 3, 38.5 milliliters. Now the second question is, what's the osmolarity of the solution? So what does that mean? What am I talking about? Osmolarity. We just learned that in this particular chapter. What does it mean? So we know the concentration is 0.5 molar. sodium sulfate. So if I have a solution of sodium sulfate, that's the label I would have on it. And that's the molarity. What's the difference between molarity and osmolarity?
It's the total amount of solute per liter.
Not quite. You're really, really close.
Doesn't the molarity have to, I mean, the osmolarity have to do with whether or not it can pass by membrane, cell membrane?
Not really. We're not getting to that yet. We're looking for the total number of something.
Osmolarity, you have to multiply to get osmolarity, you have to multiply molarity to the number of particle types.
Exactly. We need to refer to the number of particles. Precisely. Excellent. So when we have sodium sulfate dissolves, as we saw before, we get 2 sodium ions plus a sulfate ion. So if my concentration of this is half molar, what's the concentration of all this on the other side? We add it all together.
Wouldn't it be half of that too?
Half of what?
The ions?
No, because we have more ions than we do. Because here, this is just a single salt, right? Because we're measuring, because when we're making that solution, we just measure out half a mole of this salt, and then we dissolve it in a liter of water, and we're good to go. But when it dissolves in the water, it's no longer sodium sulfate, right? It becomes 2 moles of sodium ions and 1 mole of sulfate ions. So if the concentration of this is 1/2 molar, and it breaks into 2 sodiums and 1 sulfate, what's the concentration of all the particles now? Add it together.
1.
Okay.
That would be the remember the last, we just figured out that would be the concentration of the sodium. So the sodium, the concentration of sodium is indeed 1. That's 1 molar, twice as much, but you're forgetting the sulfate ions. What's the concentration of the sulfate ions?
0.5.
0.5, right. And then you add them all together. So the concentration of the sodium is 1 molar. The concentration of the sulfate ions is 1/2 molar. When we add them together, we get 1.5 molar. So how many significant digits should I put in that answer?
3.
3, right. So this is our final answer, 1.50. So basically, you determine the molarity of every species in there. When we dissolve something, what happens to it? If it's ionic, it breaks into different particles. It breaks into ions, positive ions and negative ions. Now, if I dissolved 1/2 molar of sugar in a liter of water, if I had 1/2 molar sucrose, what would be the osmolarity of that?
Sorry, I just want to make sure,
Oh, go ahead.
the reason why sodium is 1.0 molarity is because when you break the solution into the ionic, you break
Right.
it up into the ions, there's 2 sodium for
Yep,
1
two, right there
sulfate.
tells you from the formula, it tells you for every 1 mole of sodium sulfate, you get 2 moles of sodium. So when it ionizes, you get twice as much sodium as you do sulfate.
Okay.
So the concentration of the sodium will be twice as high as the concentration of the sulfate. And the concentration of the sulfate will be the same as the concentration of the salt, because there's 1 mole of sulfate ion for every 1 mole of the salt. But if I had sucrose, if I had 0.5 molar sucrose, for instance, table sugar, what would be the osmolarity of that solution?
And then just 0.5 molar.
Right. It's the same, because when I dissolve sucrose, when sucrose dissolves in water, all I get is sucrose aqueous. It doesn't break into anything else. It just becomes a solubilized sucrose molecule. So the concentration is exactly the same. Yeah, excellent. All right, so we got to go, but real quickly, sort of basically show you how to deal with the last one. So the last one, you need to, what's the very first thing you would need to do for this question? As the dogs go insane upstairs.
Start with the formula.
Start with the formula, exactly. We need a balanced equation. So one of my reactants is HCl. The other reactant is lead nitrate. And my product is, or one of my products is lead chloride. What's the other product? What am I missing?
Nitric acid.
Excellent, nitric acid, right. We take this is a double displacement reaction. So the hydrogen and the lead basically switch places. And so the lead goes to the chloride and the hydrogen goes with the nitrate. Right. So then balance it. And I think to balance it, you need to have 2 moles of hydrochloric acid. And it makes 2 moles of nitric acid. And this is our product, our precipitate. So we have that many moles. It even helped you. I didn't even make you convert the moles. So I have that many moles of product. Figure out how many moles of HCl you need using the balanced equation. And then you have a concentration here. So just figure out what the volume, using volume times concentration equals moles. That one, actually I made that one, that one's really straightforward. So I gave you an easy one for the end. I don't know why I did that. Okay, any questions about anything we've done tonight before we call it a night? No, I went kind of fast there.
Oh, it's good. Thanks.
Can you go back?
Go back to what?
You
You
erased
deleted
it too
everything.
quickly.
I was reading it.
Go back to.
You erased everything that I
All
was
the
going
work
to
that you
write.
had.
Oh, to this one?
Yeah.
There you go.
Oh, thank the Lord. Whew.
Yeah. Man, you should be able to do this.
By myself, yes. I'm just looking at it. I'm just looking at it. Okay, so it goes there. Oh, okay, I was right. Okay, cool. Thanks, Professor.
I don't suppose you have office hours before lab tomorrow, do you?
No, not tomorrow, sorry.
Oh, okay.
All right, everybody got that one? All right. It's a little past 10. All right, good night, everybody. If you have any questions, yeah, just email them to me.
Okay, good night.
Thank
Yeah.
you.
Thank you.
Thank you, Professor.
All right, I'll talk to you, most of you tomorrow.
You should